Tableau 9, Part 2. Repeated independent trials, product spaces. The thread or skein of independence runs right through the story of probability. In many ways, it is the central concept in the science. Now, thus far, we've built up an idea of independence for a pair of events. It is now time to build upon this structure and think about independence in a rather more abstract and general fashion. At its heart, the idea of independence is codified in the elementary mathematical observation that independent possibilities multiply. Let's go back again to simple settings where we have a finite number of elements and we start putting together extended multiplication tables. If you recall, in Tableau 9, Part 1, we started by looking at an ordinary multiplication table where we had two elements, a row and a column, building up an array of possibilities. Now let's move on to a setting slightly more abstract where we have three alphabets. To distinguish them, we'll use Gothic uppercase letters, fancy A, Gothic B, and Gothic C, respectively, for these three alphabets. We will deal with a certain amount of abstraction by assuming that the first alphabet, Gothic A, has got, let us say, L elements labeled A1 through AL. The alphabet Gothic B has got, say, M elements labeled B1 through BM, and the alphabet Gothic C has got, let us say, N elements labeled C1 through Cn. Now, the dimensionality is still small enough that we can visualize this, for example, by a three-dimensional cube. Imagine writing down the elements of the alphabet Gothic A along the x-axis, the elements of the alphabet Gothic B in the y-axis, and the elements of Gothic C along the z-axis. The moment you arrange them in this fashion, you observe that we have various lattice points, cubicles, grid elements that pop up. And we can think of arranging them in various fashions. So, for example, if we look at slices, for example, the XY slice, or the XZ slice, or the YZ slice, you get pairs of possibilities. And every pair is an ordered pair, one element followed by the other, which tells you all the possibilities for that slice. Now, there are three possible slices, and these give rise to three Cartesian products. The Cartesian products of A with B, of A with C, and B with C. Now, of course, there's one more possibility, an ordered triple of possibilities, A, B, C. And in this case now, we've got all possibilities for cutting and dicing these three alphabets. Our question now is, how many ways can we cut and dice in this fashion? And our very basic, elementary principle of counting tells us that the number of ways we can arrange ordered pairs A and B is L times M. It's just a multiplication table of possibilities. The number of ways we can arrange ordered pairs A and C is L times N. Again, it's an ordered pair of possibilities. And finally, the number of ways of getting an ordered pair of possibilities, B and C, is M times N. How many ways are there of getting an ordered triple? Well, naturally enough, each triple corresponds to a lattice point on a three-dimensional cube. A lattice point or a grid point, this corresponds to each of those cubicles you see in the figure. And there are exactly L times M times N such possibilities. Very basic, simple idea. The fundamental property of counting that independent possibilities multiply. We can specify each element in a pair, each element in a triple, independently of the other. Now let's immediately abstract this principle into a formal definition in a probabilistic sense. Of course, as we've seen, when we're dealing with combinatorial elements, then this counting principle immediately gives you a product rule for probabilities. We'll now abstract this to settings where the probabilities are not necessarily rational numbers, but could be generic real numbers. And this gives us a rule of products. Let's begin by looking at 3 events. So we will say that 3 events in some probability space, creatively called A, B, and C, are independent if and only if 4 relations are satisfied. The first 3 relations talk about a product rule for pairs of those 3, A with B, A with C, and B with C. The last tells you a product rule for all 3 of them together. Independence is a rule of products. And already we see that the setting is a little more complex than what we had for 2 events. For 2 events, you only have one way of combining them, A intersection B. But when you have 3 events, you have many ways, now in this case exactly 4 ways, of looking at pairs or triples of them. Now before you go on, the first 3 relations look familiar. They correspond to independent statements for pairs of events. If the first 3 relations are satisfied, then we shall say that the events A, B, and C are pairwise independent. But pairwise independence, as we shall see, does not in general imply independence in the sense that all 4 relations are satisfied.